He's now in the Department of Physics, and we're both part of the Center for Quantum Science and Engineering at Stevens, which is something that is growing up right now. So the problem we're dealing with, we wanted to deal with something easy first. So we're dealing with portfolio optimization, and we use the classic framework of portfolio optimization. This is the Markowitz portfolio optimization model, basically what's going on in here. So basically, here you minimize the risk subject to a set of expectations, okay? And this is a problem we want to solve. It's a very well-known problem. And we want to apply this in a little bit slightly different context. So we changed this measure of risk, which is here the variance of the returns, and we applied to this a different type of measurement of risk with something that we call a risk function. And this is the problem that we solve. Okay, we are minimizing the risk of the losses. That's why you have minus there. This is the negative of the returns, which transfers into the losses. Subject to, now here the constraint is just that the investment is completely done. We are investing all our wealth. Now, this is a much more harder problem to solve. Okay? The previous problem, you can basically, because we have here variance and expectation, you can take the data that you have and kind of compress it and just solve a problem, basically without having to look so much into the data. You can focus on the statistics of the data. When you have a problem like this, because this function depends on the data itself, you no longer can rely on these statistics. Okay? There will be some statistics that you can use, but actually you have to use the data. Okay? And it becomes a much more difficult problem. It becomes a huge problem, and it's not going to be linear, just like the previous one. Now, which kind of risk measures we use? Here we have a list of them. Expectation, it wouldn't be useful, but yes, it's one of those. C-bar, conditional value risk, we can use exponential utility, mean deviations, and so on. Actually, it's an infinite family of these risk measures. Each one of these risk measures, basically what it does is that it considers the random structure of the problem and tries to analyze and assign some value of risk depending on how they are constructed. Now, we can solve this problem, theoretically speaking, into a much more complex system in which we have dynamics, okay? So basically, you have a series of actions. If portfolio optimization will be rebalances through time, and then you're considering the risk, your decision today, but considering the risk along the stream of actions that you will be taking in the future, okay? And the problem looks like this. It's very hard to solve, okay? Now, and this is what we would like to be able to solve. At the moment, we have to consider just one step risk. We can solve this without quantum computing. It takes a lot of time to solve, but eventually we will get to this one using quantum computing. At the moment, we are just not there. Okay? But the key thing is that a while ago, we proved some theorem about this formulation for the general problem. And it turns out that we can take that complexity-looking problem and make it look something like this, which basically the evaluation of risk turns out to be the maximum over the worst kind of possibilities that happen in some special set. And then this problem becomes some minimax problem that in many cases is quadratic. And this is the connection with the quantum computing part. Because it turns out that this kind of quadratic problems actually can be solved with special type of quantum computers. Okay? And that's where we have this connection. So just to talk a little bit about the quantum computers, what we rely on is not on the general purpose quantum computer machine. We're relying on this adiabatic quantum computing. And it's all based on this algorithm. Okay? The whole idea of the algorithm is that we encode basically we're going to be considering some different problems, optimization problems, and we're going to be considering encoding our solution will be also the solution to this problem, difficult problem that quantum computer considers. So essentially what we want to do is we want to solve, let's minimize the losses through this risk method, and we encode it into these Hamiltonians. Okay? And quantum computing, adiabatic quantum computer, basically what it does is that we start with a simple Hamiltonian to solve, and then through some physics equations, we transfer from that problem to our final problem, which is the actual problem we want to solve. And turns out that because of the magic of quantum physics, if we have, from the beginning, so let's suppose the left is the initial problem, the right is the difficult problem we want to actually solve. So we start with the initial problem. It's trivial to find the solution. We slowly move one to the next. Okay, this is what the quantum machine does, actually. Once we reach the ending point, we have the solution. It's like the solution kind of transfers for us. Okay? So it's kind of magic in the sense that we are not developing a solver to solve these difficult problems. It's just the quantum phenomena give us that. Okay? And this theory is very old, actually. This is some of the very first things that people did with quantum. It was not used originally in any context of quantum computing. It's just something that happens. It's called adiabatic paths. It's just something that is known since the 50s or 40s, something like that. So it's very old knowledge that now, because we can produce these machines, it can be exploited. So in order to do this, these Hamiltonians, they need to have certain very specific properties. And actually, what happens is that we can prepare them if they are relying on these pseudo-Boolean functions, which are 0-1 functions, which are very good for applications because we can model our applications with this 0-1 type of optimization problem, and we can use it. So this pseudo-Boolean, here is just showing you like all the theory behind that allow us to create these Hamiltonians. So this is something that people have been working on for many years. So, but we don't really need to work on at this level. What we do is that we consider our problem now, and we fix a risk measure. In this case, is this guy, this mean upper semi-deviation. It's just a risk measure in which you consider your loss, and then you calculate the expectation of the losses, and then you'll be applying some sort of penalty for any time you go above the expectation in the loss. And then you try to minimize that. If you think about it, it makes sense because you will be kind of like minimizing the losses in a way that actually the part where in the loss that is below the loss doesn't get penalized, which is good. So the problem we want to solve actually looks like this. And because of the theorems that we know, and some of those we have been involved into, we know that this problem turns out to be some sort of minimax problem. And then a lot of what we do is to transfer this optimization problem into the context of this pseudo-Boolean optimization to obtain these Hamiltonians that we give to the machine, and the machine will solve for us. Okay? And this is what we have next. So in a series of steps, we increasingly manage and change the problem from the original shape into by using equalities. You know, every time we find a problem that is equivalent to the one that we had before, but we represent it in a different way, and we keep doing this. We have to remove the constraints, so we move the constraints to the objective function via penalty functions. This is classic kind of stuff. And then we analyze the penalty function because it's the objective function with the penalty function, which gets very complex. And we simplify a little bit. We create these matrices. And the end result is that we can say, OK, our problem, looks like this. From here, we have to make it binary. So we add some matrices that will take care of conversion between numbers and binary numbers. The binary values are the ones that come out from the qubits that we're going to be using. And we create these complex matrices, and then this is the problem. Okay? So after a lot of work making this transfer, we obtain a final program, and the program that we give to this machine is nothing but these matrices, like this G matrix and this GQG. Those two matrices, that's the program itself. So we give this to the machine prepares the quantum system, and it will solve it for us. Okay? The amount of time it takes to solve is actually not much. The problem is that these machines are random. Okay? So if we solve once, we won't get a solution. We have to solve many times. Okay? And what I will show now is some results. I more or less explain the kind of things that we see and what we can do and where the research actually points us to what should we do. Okay? The first one is size. These problems are relatively small, the ones that we can solve directly into the machine. So the first thing that we want to focus on is developing problems that allow us to take huge problems and decompose them such that we can send them to this machine, and we're working on that. That's actually one of the difficult things we need to focus on. Now, here we have two examples. On the left is some optimizations that we did using different type of methods on that machine for 100 runs, and then we run it again for 1,000, and we compare more or less the values we get. This is not so useful because it's difficult to read, so I will show you some graphs about this. But when I was talking about the size of a problem, there is an important issue with these machines, is the interactions between the variables and the components into the problem itself. Okay? So we can make a graph where we have all the variables are the nodes, and then if two of these variables appear together as a quadratic term, we add an edge between them. And this is a graph that we obtained for a 48 by 48 type of problem. It's actually a small problem. Once we start adding all of these variables, it looks like this. Now the machine has some physical constraints, and this is for the D-Wave 2000 machine that has over 2,000 qubits. Okay? We have to place this graph on this other graph, okay, via embeddings, topological embeddings, sorry. And turns out that what it does is it takes a problem of 48 or some variables and basically takes thousands of, because you have to multiply them, and the thing just becomes tricky. And actually solving this problem, this is something kind of funny, that solving this problem is MP hard, to solve it fast, okay? So even if we do all the other part easy, we still have to solve this problem, which will be really hard. Okay, we have ways of doing it, but not in the most efficient way. Okay. So we will take this problem, embed it into the machine into this way by doing this topological embedding, and then we can solve the problem. So this is a big problem, a big area where if you find a better algorithm to do this embedding, that's again an improvement on these machines. Now, the results we obtain, this is for one of these problems where we run it just 100 times, and we have here the objective value is on the x-axis, and then we have some frequencies of observations. You see, they look like they're stacked on top of each other. They are not stacked, it's just that the dots are too wide and they look like on top of each other. So you see, we observe these are the values that the machines told us that were the optimal values. There's a big difference, no? Here there is minus 3,290, and here we have minus 3,250. I mean, what happens is that, yes, these machines are random. Their noise actually damage what you're observing, so you have to run them many times. And here we have another one for another type of problem. You see, it's clear that it's actually finding something, but we have here two sides, no? What happens here is that these are interior optimization problems, and there are two local solutions. So this is better than that one, so this is one that we want. Okay? And here we run this many more times. This is a 10,000 times run, and then we have the frequency of the observations. Okay? Actually, for us, we could just take the last point that we see here, and that's the best solution that we obtain for this problem. Okay? But we observe all of these. Okay? It's a big problem because we need to use statistics to make sure that we won't get something better. Okay? So again, this is another area of research that we have to focus to understand how these machines actually work. And this is for a different problem. Depending on the problem, how you configure the problem and you put it into the machine, you get different frequencies. Like, this is better. This is what you would like to see, where actually you see much more often the actual value. This is a problem where the solution was 0. And we know what the solution is because we solved the problem via other methods, so we know the actual solution, and then we can compare and see if we're doing the right thing. One of the last things is this. Here what we have is we have looked at the time series of the samples that we are, many times we're solving, 10,000 times. And then this is the observed values. Okay, they look, again, on top of each other. They're not really like that, but because the width of the dots. And a key observation is that actually the distribution looks the same across time. Okay, at least for this problem. Actually, there's some other problems that it doesn't. So if we do things right, we shouldn't need to run 10,000 times to discover the solution. Maybe to run it like a few hundred times would be enough. And actually, that would be a big difference in runtime. Okay? And here we have marked the best solution and the worst solution up here. So there's a huge range there. The last thing, and this is, again, kind of the things that we can do to improve these machines is that we can add some physical tricks In this case, we can add a pause in the computation. This literally is a machine that is doing something physical, and you can just stop it and then continue. And turns out that improves very much the quality of the results. I'm sorry that this picture is not great. I need to change the colors, but the whole idea is that here on the x-axis we have the amount of time we are adding a pause, okay? And actually not the amount of time, sorry, at which point we're adding a pause in the development of the problem. And here we have the percentage, how well we're approximating the actual solution. So lower is better. And in every case, we see that a pause around this 0.6% of the total runtime actually improves the computation. So why this is important? Because the improvement is dramatic. And there are some other research that they have been doing which shows similar. And the whole point is that now we in academia, we can look into theories that actually support this. And there are some reasons for this, but there are some other tricks that people are doing that are actually working to improve these solutions that require a lot of research to understand what's going on. So, I mean, I hope you guys get an idea of the kind of things that we're doing. Now, this is, as I said, this is the beginning of a lot of things. And just for comparison, the key thing is that now we're solving this with almost toy problems. And it takes, all of this happens in just 1 second or whatever, maybe less. The whole point is that it should take the same amount of time if we are dealing with millions of variables. And that's the point where this is going to be very valuable, because solving that big problem with millions of variables will take me a month, as I mentioned before. So, and here, this could take just a matter of seconds. And then at that point, we could use this, leverage this into some other services that we could just build for finance. That's all. If you have questions, I'm willing to answer them.
To provide that information as a market signal is something we haven't been able to do, so I'm very excited to see making these computational advances, because it have huge implications for information services for financial markets.
Yeah, and that's the thing, that for that type of system where this information should be obtained immediately or fast enough, this is what we need to do. I have Rupak, my collaborator. He used to work in, I think it was American Express or Citibank, and he used to be on the risk department. And he will tell me, "Oh yes, we will put some of these things to run in a way simpler model, and it will take, they will do it on Friday, so on Monday they will have, the results." And real-time decisions cannot be made like that. So yeah, that's part of the things we want to do. Thank you, guys.